The equipment grounding conductor, or EGC, on heating, ventilation, and air conditioning, or HVAC circuits should be sized based on the motor circuit ampacity, or MCA, and not the size of the circuit breaker installed. NEC 250.122a requires that the EGC for equipment be sized based on the overcurrent device protecting the circuit. However, NEC 440.22 specifically states for motor circuits, and I quote, "The ampacity of the equipment grounding conductor for a motor branch circuit shall be not less than the ampacity required by 250.122a, but not less than that of the circuit conductor required by 440.21b." End quote. NEC 440.21b requires the circuit conductor to be sized based on the MCA of the motor. Therefore, the EGC for HVAC circuit should be sized based on the MCA of the motor, even if the circuit breaker installed is larger than the MCA. This ensures that the EGC provides adequate protection in the event of a ground fault. Here's an example. A 7.5 horsepower, 230 volt single-phase motor has an MCA of 35 amps. According to NEC 250.122a, a 30 amp circuit breaker would be required to protect the circuit. However, since the circuit is a motor circuit, the EGC must be sized based on the MCA of the motor, which is 35 amps. Therefore, an 8 American wire gauge, or AUG, EGC would be required, regardless of the size of the circuit breaker installed. Here are additional considerations. Firstly, if the cabling method used for the circuit conductor has a higher ampacity rating than the MCA of the motor, the EGC does not need to be increased in size. Secondly, if the cabling method used for the circuit conductor has a lower ampacity rating than the MCA of the motor, the circuit conductor and EGC must be increased in size to match the MCA. In summary, when dealing with HVAC circuits and sizing the equipment grounding conductor, or EGC, remember to prioritize the motor circuit ampacity, or MCA, over the circuit breaker size. NEC 250.122a generally dictates sizing based on the overcurrent device, but NEC 440.22 provides a specific rule for motor circuits, including those in HVAC systems. This rule states that the EGC must be at least as large as required by 250.122a, but not less than the size of the circuit conductor required by 440.21b, which is based on the MCA. The importance of adhering to the MCA for EGC sizing lies in ensuring adequate protection during ground faults. A properly sized EGC provides a low impedance path for fault current to return to the source, facilitating the quick operation of the overcurrent protective device, like a circuit breaker, and minimizing potential damage or hazards. To illustrate this further, let's consider another example. Imagine a scenario with a 10 horsepower, 480 volt, 3-phase motor used in an HVAC system. This motor has an MCA of 14 amps. The circuit breaker protecting the circuit is a 20 amp breaker chosen to accommodate the motor's inrush current during startup. Now, when sizing the EGC, you might initially think of using the 20 amp breaker size as the determining factor. However, because it's a motor circuit, NEC 440.22 takes precedence. Therefore, you must size the EGC based on the 14 amp MCA. Referring to NEC 250.122b, we can determine the appropriate EGC size for our 15 amp overcurrent device, which is the next size up. In this case, a 14 American wire gauge, or AUG, copper conductor would be sufficient for the EGC. This example highlights the potential for using a smaller EGC size when following the MCA-based rule compared to sizing it based on the breaker. It's important to always consult the relevant NEC tables and ampacity charts to determine the correct EGC size for a given application. Now let's delve deeper into the additional considerations mentioned earlier. The cabling method used for the circuit conductors can influence whether you need to upsize the EGC. For instance, if you're using a cable with a 90 degrees Celsius insulation rating and the terminals are rated accordingly, you might find that the cable's ampacity is higher than the motor's MCA. In such a case, you would not need to increase the EGC size beyond what's required for the MCA. However, if the cable's ampacity is lower than the MCA, you must increase both the circuit conductors and the EGC to match the MCA. This ensures that all components of the circuit can safely handle the motor's full load current. It is important to understand that the NEC permits the use of overcurrent protection size to handle motor starting currents. These currents can be many times larger than the motor's full load current, or FLA. This is why you will often see overcurrent protection circuit breakers or fuses substantially larger than the motor's full load amps or MCA. The MCA includes 125% of the motor full load amps plus the sum of the full load amps of other loads such as contactor coils. When sizing the EGC, do not use the motor full load amp value, always use the MCA value, as it is required to size the circuit conductors. The EGC protects the circuit equipment and personnel in the event of a fault. The equipment grounding conductor carries fault current back to the source, tripping the overcurrent protection and clearing the fault. A properly sized EGC is also critically important for sensitive electronic equipment. A properly sized EGC will reduce electromagnetic interference and ensure proper operation of sensitive equipment. In summary, sizing the EGC in HVAC circuits requires careful consideration of NEC 250.122A1 and 440.22. Always prioritize the MCA of the motor when determining the appropriate EGC size. Remember to consider the ampacity of the cabling method used for the circuit conductors. By following these guidelines, you can ensure that the EGC provides adequate protection in the event of a ground fault, safeguarding equipment and personnel. Let's explore some advanced scenarios and address potential misunderstandings related to equipment grounding conductor or EGC sizing in HVAC systems. One common misconception is that the EGC size can be reduced proportionally if the overcurrent protection is significantly oversized. While it's true that NEC 250.122b allows for a reduction in EGC size under specific conditions, this provision does not apply to motor circuits governed by NEC 440.22. The MCA-based sizing rule takes precedence, regardless of the overcurrent protection size. Another critical aspect to consider is the type of EGC used. While copper is the most common material, aluminum conductors are also permitted under certain conditions. When using aluminum EGC, it's essential to refer to NEC 250.122b to determine the appropriate size, as aluminum conductors have different ampacity ratings compared to copper. Furthermore, the path of the EGC is crucial for its effectiveness. NEC 250.45 emphasizes the importance of providing a low impedance ground fault current path. This means that the EGC should be installed in close proximity to the circuit conductors, minimizing the loop impedance and ensuring a rapid response from the overcurrent protective device. In practical terms, this often involves running the EGC inside the same conduit or cable as the circuit conductors. It's also important to avoid creating unintentional ground loops, which can interfere with the proper functioning of sensitive electronic equipment. Ground loops occur when multiple ground paths exist, creating circulating currents that can introduce noise and disrupt signal integrity. To prevent ground loops, it's best to establish a single point ground for the entire system. In addition to the sizing and installation requirements, regular inspection and testing of the EGC are essential for maintaining its effectiveness. Over time, connections can loosen, corrosion can occur, and conductors can become damaged, all of which can compromise the integrity of the grounding system. Regular testing, such as continuity testing and impedance measurements, can help identify potential problems early on, allowing for timely repairs and preventing costly downtime or safety hazards. Now, let's consider the implications of using variable frequency drives, or VFDs, in HVAC systems. VFD introduce harmonic currents into the electrical system, which can affect the performance of the EGC. Harmonic currents are non-sinusoidal currents that can cause overheating, voltage distortion, and equipment malfunction. To mitigate the effects of harmonic currents, it's often necessary to use an oversized EGC or to install a separate, dedicated grounding conductor for the VFD. Additionally, shielded cables and line reactors can help reduce harmonic emissions and improve the overall performance of the system. Finally, let's address the issue of grounding electrode conductors, or GECs. GEC connect the equipment grounding system to the earth, providing a path for fault current to flow back to the source in the event of a ground fault. The size of the GEC is determined by NEC 250.66, which is based on the size of the service entrance conductors. It's important to ensure that the GEC is properly sized and installed to provide an effective ground connection. In conclusion, mastering the nuances of equipment grounding conductor, or EG, sizing in HVAC systems requires a thorough understanding of NEC 250.122A and 440.22, as well as careful consideration of various factors such as cabling methods, conductor materials, harmonic currents, and grounding electrode conductors, or GECs. By adhering to the code requirements and best practices outlined in this discussion, you can ensure the safety and reliability of HVAC electrical systems. Consider a specific case study involving a large commercial building with a complex HVAC system. The system incorporates multiple chillers, air handling units, and pumps, each with its own motor and associated electrical circuitry. The design engineer is tasked with ensuring that the equipment grounding conductors, or EGs, for these circuits are properly sized and installed. The engineer begins by identifying the motor circuit ampacity, or MCA, for each motor, using the motor nameplate data in NEC 430.24. They then refer to NEC 440.22 to determine the minimum required size for the EGC based on the MCA. In some cases, the engineer finds that the circuit breakers protecting the motor circuits are significantly oversized due to the need to accommodate motor starting currents. However, they correctly recognize that NEC 440.22 takes precedence, and the EGC size must be based on the MCA, not the breaker size. Next, the engineer considers the cabling methods used for the circuits. They are using a combination of rigid metal conduit, or RMC, and cable trays. For the RMC installations, the conduit itself serves as the EGC, providing a low impedance ground fault current path. For the cable tray installations, the engineer uses a separate, insulated EGC sized according to NEC 250.122b. They ensure that the EGC is installed in close proximity to the circuit conductors, minimizing the loop impedance. The engineer also pays close attention to the grounding of the VFD used to control the speeds of some of the motors. They install separate, dedicated grounding conductors for the VFD to mitigate the effects of harmonic currents. They also use shielded cables and line reactors to reduce harmonic emissions. Finally, the engineer verifies that the grounding electrode conductor, or GEC, is properly sized and installed according to NEC 250.66. They ensure that the GEC is connected to a suitable grounding electrode system, such as a ground rod or a building steel. Throughout the design process, the engineer meticulously documents all of their calculations and decisions to ensure compliance with the NEC and to provide a clear record for future maintenance and troubleshooting. By following these steps, the engineer is able to design a safe and reliable grounding system for the HVAC system, protecting both equipment and personnel. Let's move beyond the basic principles and explore some of the less obvious but equally important aspects of EGC sizing and installation in HVAC systems. One often overlooked area is the impact of voltage drop on the performance of the EGC. Voltage drop occurs when the voltage of the load is lower than the voltage at the source due to the impedance of the circuit conductors. Excessive voltage drop can reduce the effectiveness of the EGC by increasing the impedance of the ground fault current path. To minimize voltage drop, it's important to use appropriately sized circuit conductors and to keep the circuit length as short as possible. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Another critical consideration is the bonding of metal components in the HVAC system. Bonding is the process of connecting metal components together to create a continuous electrical path. Proper bonding ensures that all metal components are at the same potential, minimizing the risk of electric shock. NEC 250.92 requires the bonding of metal piping systems, metal air ducts, and other metal components that are likely to become energized. The bonding jumpers used for this purpose must be sized according to NEC 250.102. In addition to bonding, surge protection is another important aspect of protecting HVAC systems from electrical transients. Surges are sudden, temporary increases in voltage that can damage sensitive electronic equipment such as VFD and programmable logic controllers, or PLCs. Surge protective devices, or SPDs, are designed to divert surge current away from sensitive equipment, protecting them from damage. SPD should be installed at the service entrance and at any sensitive equipment locations. When selecting SPD, it's important to choose devices with appropriate voltage and current ratings for the application. Furthermore, it's essential to follow the manufacturer's installation instructions carefully to ensure that the SPD are properly grounded and bonded. Another factor to consider is the presence of corrosive environments. HVAC systems are often located in areas where they are exposed to moisture, chemicals, and other corrosive substances. These substances can damage the EGC and other electrical components, leading to reduced performance and potential safety hazards. To mitigate the effects of corrosion, it's important to use corrosion-resistant materials such as stainless steel or copper for the EGC and other electrical components. It's also important to apply protective coatings to exposed metal surfaces. Finally, let's address the issue of documentation and labeling. Proper documentation and labeling are essential for ensuring the safety and reliability of HVAC electrical systems. The electrical drawing should clearly show the location and size of all EGC. The electrical panel should be labeled with the circuit numbers and the corresponding equipment served. All electrical equipment should be labeled with the voltage, current, and power ratings. By following these guidelines, you can ensure that the HVAC electrical system is properly designed, installed, and maintained, providing safe and reliable operation for years to come. The NEC is updated every 3 years. Always consult the most recent version. The local authority having jurisdiction may also have local amendments to the NEC. Always comply with any local requirements in addition to the NEC requirements.